Welcome back to the SYSWELD Masterclass series. In the previous video, we explored the basics of welding simulation with 2D models covering manual metal arc welding and resistance spot welding from setup to results. Now it's time to take things to the next level. In this intermediate tutorial, we'll build a full 3D model and focus on investigating residual stresses. Step by step, you'll see how to create the geometry, define the mesh, apply the heat input, and finally analyze the stress distribution left behind after welding. By the end, you'll not only understand how to set up a 3D SYSWELD model, but also gain valuable insights into residual stress prediction for real-world applications. Let's get started. In this tutorial, we want to go one step further and perform a 3D manual metal arc welding simulation. In this tutorial, you're going to learn how to create a 3D model which is different from the 2D model. Obviously, we're going to perform thermometallurgical analysis of a manual metal arc welding. You're going to work on phase transformation analysis and post-processing the results, like exporting the curves and exporting the videos and do some cool stuff. The material we're going to study in this tutorial is 316L stainless steel, and in this slide you see the model's dimension. This is a material, a sheet material, a 5mm thick sheet material, width of 30mm and the length of 60mm, but the welding is going to be on the transverse direction. So the coordinates of the model is presented in this slide. It is pretty useful while we're doing the simulation and we want to create a model. We should have a map of our model. I suggest that you always write down these coordinates for you, whether you're going to simulate or regenerate some of the models from articles or some scientific papers. You should always have this map for you. And the material phases are presented here. The first phase is austenite, and while we're doing the simulation and thermal analysis, it's going to turn to ferrite, and the second phase, as always, is a filler material. So the heat source is the same, it's a gold die because we're going to do the manual metal arc welding, and everything else is pretty much the same. The major difference is the model creation. Alright guys, now we're going to create our model in Visual Mesh, so click OK. Here it is, the Visual Mesh. We click on New File and create our coordinate. As always, we go for Node and create by XYZ locate. First coordinate is X0, Z0, which is the first one, and we're going to have the X60, Z0. We're going to create X60 and Z45, and we're going to have 27.5, we're going to have 33.5, and we're going to have 30.0. I think that's it, or we need one other coordinate. Let's switch back to this view. Yeah, we need X0 and Z5 and hit apply. So in the view section, I already did uncheck the model coordinate system here, but you can have it if you want, so don't freak out if you don't see this one. Alright, it's pretty much our model. Let's double check. We have this one, 27, 33, 30, 60, and that's it. Now we're going to create a 2D model with 3/4 point mesh, and let's do the weld first, and that's it. The element size, let's say 1, and see what happens. 1 is not good enough. Let's make this edge let's set this as 10, and these two guys should be 9. Yep, that's good. So we keep this mesh, create mesh, and click OK. And then we're going to select our base metal section. There we go. So we're going to set this edge as 9, and we can set these two as 12. And let's do the biasing, linear bias and bias edge, this edge and this edge, and we're going to flip this one. I go faster right now because it's pretty much the same as the previous video. So I click OK. This looks good. Let's make this more visible, and here we have the other part. And mesh, we are going to do the same thing, 9 and 12, and this one for 9. Let's bias this edge and this edge, and flip the bias for this edge, create mesh, and here we go. So here is a 2D model we created, and it looks good. We don't need fine mesh here, so we coarse mesh is okay here because the heat is pretty much here, and when we have good size elements here, so it looks fine. Alright, so the difference between the 3D model and the 2D model, which starts from here, we're going to select the weld zone, holding shift to unselect, and we can just click on the weld part to select this one, and we right click on the weld part, and we're going to add it to a new part, which is this one. Alright, now we're going to make this 2D model, let's turn this 2D model to a 3D model. So we should go to the 3D tab and select the sweep or drag. Alright, the idea of this sweep is to select some faces and sweep them into a direction or a vector which is in our favor. So I'm going to hide that part and only make the weld part visible, and the first thing to do is to select the element faces. So we are selecting our elements, and we can click here to update faces. Now the faces are updated. From this part we're going to select a vector. I'm going to select the standard axis because we're going right now we are in ZX direction, and we are going to sweep this material and extend this material into the Y direction. So I select standard axis, and I'm going to select the Y axis as well, and this should be global. And if we rotate the model by holding A, so by holding this A, you can create we can rotate the model and see here is the vector we are going to sweep or drag our model into. So this is in the direction we want, If you want to do the other direction, you can simply click on flip and that's it, but we want this to be in this direction, so we click OK, and the distance should be 30 because our model, the length of our model is 30 millimeters. So here you see is the expectation of the model, so this is going to be extended in this way, and we click on create mesh. Now we're going to select our seeds into this direction, so let's keep this one as 60. We can do the biasing, do everything else we want, but right now it's okay. We want 60 elements on this length, and if we click on mesh volume, we see our mesh is not created yet. We cannot see that actually, but you can kind of see whether is the model is in your favor or not. Or let's modify this. If we want it to be smaller, we can make this as, for instance, 90, and we see how our mesh is going to be. I think 60 is fine, so I'm going to keep this and click OK, and now our mesh is created. So as you see, this is a new part containing all of our new elements which are in 3D. So here we have the 2D face, and this is our new 3D model. So we're going to rename this one. I'm sorry. We right click and we go to the part manager and we rename this one as weld. Alright, so I'm going to make this part visible. We don't need the weld right now. Alright, I'm going to do the same thing. In the 3D tab, I want to sweep and drag, and now I'm going to select the element faces. These faces are selected, everything else is in the correct order, so I'm going to click on mesh. I'm sorry, I have to select this element and have to update faces, then I click OK, and here we go. We can mesh. So that number was 60, and if we want it to be a correct mesh, it should be 60 as well. So we click OK, and the mesh is okay. Alright, we have a new part. We can rename this one as the left hand side. So we go to the part manager, we select this one as left. It's pretty useful if we want to do a dissimilar welding. We can assign different part, so we can assign different material, I'm sorry. So we're going to make this one invisible, and we're going to select 3D, sweep drag to do the other part. So I'm going to select this part, right hand side, update faces. You can select it either from here or here, and we click OK, then it is created, and we say mesh and 60. Okay, Now we have our new part. So this part should be renamed. So let's say right. Okay, right now we have 3 parts: left, right, and the weld. Simple as that. We can create a 3D model, so we don't need these 2 parts. So let me show you these parts. These parts are the 2D model. We can delete them, or we can keep them as they are. I rather not to delete them originally, because maybe our meshes are not good and we want to modify that, and we want to do the sweep and drag again, so we need these 2 parts. But I'm going to maybe hide them. Yep. Alright, so the next thing to do is to go to the checks and select the coincident nodes. As you see, we have thousands of nodes that are coinciding on each other, so we say coincide all and fuse all, then apply. Now we're going to check that again, and we see there are no coincidence node. So I click close this dialog, and the next step is to do the heat transfer. Do the heat transfer part. So in the previous video we went to 1D and we extracted the boundary of the heat transfer from the 2D mesh, but right now we should go to the 2D and we can extract from 3D mesh. Alright, here we have we can select our element faces. I'm going to select all of them, but here we have 2 options. We have one open faces and one all faces. I'm not going to select all faces because inside the bulk is going to be selected if I choose all faces. So this size of let me show you. If we see the weld inside, this size are not in contact with the environment, but if we select that, it's going to even select inside the weld, which is not correct. So we're going to leave it as open faces, selecting all of them, extract 2D, and this is selected, and we hit apply. Now as you see, we have a new part. If we unselect all of them, we see that these are the parts are selected, and are hollow inside. This inside the bulk and inside the weld is not selected. Alright, so I would like to put that on isometric view. Let's rename this part. From part manager we can rename this one as heat env, and it's okay. Alright, the last thing to do is to select the nodes required for the clamping condition. I'm going to rotate this one here to the back of the model, and from here I'm going to select the node, and I select this node and this node. We have to make sure that we selected the correct node. So the nodes are selected, and I'm going to right click anywhere, add to new collector. So we have a new collector here, and I want to rename this one. I'm sorry, from the edit we rename this one as UXYZ because it's going to be clamped, and we're going to apply a boundary condition on all direction. The next clamping condition we're going to choose is slightly different. We're going to first we click on anywhere on a screen to ensure that we haven't selected anything. Now we're going to select this node here and this node here. Yes, it is. And tool, add to new collector. This collector, we want to clamp this one on only Z and X direction, and we're going to select the last two, which is first we have to click on the screen to unselect all those nodes. We click on this one and this one. Right, two nodes are selected here. I'm going to right click, tools, add to new collector, and edit this one, and this is only clamped in Z direction. So that was pretty much everything. I'm going to making sure that I selected the right clamp condition. From view, I'm going to uncheck this model coordinate. This is the U XYZ, this one the U Z and X, and this one is the UZ. Alright, that's it. Now it's time to save our model. So we can either do the shortcut of Control S, or we can select it from file and save. So I'm going to save it on the folder here, SYSWELD, new folder, and let's say 3D MMAW, and here I'm going to select 3D MMAW. Now the model is saved. Now it's ready to go to the next part, which is the welding parameters. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any question, just ask me in the comments down below. I respond to every single one. Thank you. Okay, now it's time to go to the visual weld. Alright, so we're going to open our file. I'm going to the SYSWELD 3D MMAW and the VDB file. I'm going to open. Here it is, our file. Now the first thing to do is to go to the welding trajectory. Okay. Now as you see here, we are under 3D model, and we are going to start select our start node. So how many nodes do we have here? 1 2 3 4 5, and here we have 1 2 3 4 5. So this one is going to be our starting node from the middle. Here we have 1 2 3 4 5 on this side, and we have 1 2 3 4 5 on the other side. right? It's exactly in the center, and right now we're going to select our reference, which is should be on the corner of the weld. So this is our first and start node path and the reference. We're going to confirm this is the welding start and the reference start, and now we're going to rotate and do the same thing here. I believe this one is the start one. 1 2 3 4 5, yeah, true. And I'm going to select this one as a reference. So this is welding end and reference end. So let's switch to the isometric view, and here we see the preview of our weld path and the reference path, which is great. Now I'm going to apply it and it is okay. Alright, now it's time to go to the welding advisor. Alright, I would like to name it 3D MMAW, and the working directory should be the same. And let's go to the solid, and it's okay, this one solid should be solid, and we can go to the material selection. Okay, now we select our components from here, 316L, and we're going to select left, and we can hold control and select right, and it's okay. Then add. Now we have our models that assigned, our parts that assigned with the 316L. Now we're going to select joins with filler, 316, and the weld. Alright, now we have to add this one. Now we're allowed to go to the next part. We are going to select the general arc, which is exactly the same as the manual metal arc. Right now we're going to select the weld line. This is the weld line, and we are going to select the filler weld and the weld group. Okay, we can go next. The velocity should be 3.5. the initial time is 0 and the total time is this. We're going to set this one as 10, the width of 6, and the penetration of 5. And I'm going to explain something to you here. Imagine we are going to simulate a real welding process, and we might not have the actual energy, but in joule per millimeter, and they are going to give us the measurement in watt. And the thing we can do is to divide the energy in watt over the velocity, and we are going to have our energy. So I'm going to open the calculator, and let's say we are going to do that with a 2200 watts, and we divide that by 3.5, and we are going to have this number. So this is our units in joule per millimeter, so 628.5066, and we can add, it says invalid penetration value. Let's see. Alright, the value should, when you click on the other one, is going to be okay, so it should be in decimal. Here we see the gold duck ellipsoid, which is okay to me, and I think we're good to go to the next part. We are going to select the heat environment. So this is the heat environment, and we click add. Now we're going to the cooling condition, and I would like to select 25. Oh, oops, it should be 0, and the final time should be 2500, and it's okay. Now we go to the clamping condition. Alright, I'm going to select X rigid, and I'm going to select all, and I select XYZ. Now I'm going to select X and Z, and I select this one. Now I'm going to select only Z, and I select this one. Now add. Oh, I'm sorry, I have to do that one step at a time, so we're going to go through it again. So XYZ, all, this is it. This one is only Z, and we're going to select XZ, this is it, XZ, XYZ, and Z. Alright, so in clamp I'm going to select all of them by holding Control or Shift, and I can select all of them here, and 2500, then add. This is the clamping conditions, and we can go through the next step. Alright, here I'm going to talk about the function database. Here we have a function database. If we click on this, we see we have a FCT file. We can open it with Notepad, and you see there are a bunch of different explanation here. This is the explanation from the previous video we had, which are for the gold duck, double ellipsoid, but here we have other things here. We can modify, for instance, the QF and QR from here and use this function database. You can modify lots of things. Take your time and look at this file. If you want to do that for your project, you can modify this file and select it. Alright, here we still don't want to do the mechanical for this video, and say generate input file. The input file is generated, as we can see here, and we select the solve 3D MMAW, open thermometallurgical, compute, and let's do this. As you see here, is turned blue, which means it's doing the calculations, and while it turns green, it means the results are ready. So if we click on this one, we can see the log file, and in the folder that the results are created, you can go and check that one step at a time for like large size simulations that are time consuming. But right now we can wait for it to finish. It should be ready anytime soon. Alright, this is finished. Now we can go and see the results in the visual viewer. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any question, just ask me in the comments down below. I respond to every single one. Thank you. Alright, we're good to go to the results section. So we go to the visual viewer. Alright, from open file we go to the 3D MMAW results, and we go for post on post 1000 FTB, and here is our model. We want to go to the temperature node results and temperature node. Okay, as you see here, the highest temperature during the process reached to the 2300 roughly, and we're going to play the animation to see how it moves. Okay, I want to stop and go to the other side of the weld. So let's set this one on 1500, or better say 1400, which is the melting point of the 316L. It is between 1357 to 1400. Now here it is, and as you can see here, it is fully melted, the root pass, and so the root of the weld is fully melted, and we can conclude that these parameters are good parameters of welding. So let's see the video, the animation once more from here. So here it is, the moving heat source and the torch of the welding. It moves from this side to this side, and then we wait for the cool down until it uniformly cools down to the room temperature. Yeah, that's it. So imagine that we want to export this video. What we can do is to go from here to file, and we can select the save image /movie /report. So here we can select this one on image or movie. We can choose the format of the file. Let's say it's animated GIF, and we hit on save, and we select the destination of the file, then save. We can choose the frame per second or the FPS, everything else. Now he said it's succeeded, and we can open it from here. As you see here, it is the heat source is moving, and there are other informations here. Right, so if you want to increase the speed of the animation, we can change it from here. So if we want it to move faster, we can change it from here. It goes faster, slower, or anything you want. Alright, now let's go to the middle part. It's kind of in the middle. Right now we want to import and plot. We want to go to the import and plot. So from here we can do some cool things, like exporting the graph of temperature versus node. We can select the node, so let's change this one to the top view, and or we can go to the final time of the weld, like here as we are. Let's say here, and we want to see the temperature versus second. You can select the node, for instance, one here, one here, one here, and we can see a gradient of the node, so we want to plot it. Now here we see the details of this file, or you can export this one, export curves. Here you can export it in CSV file, and it is tab delimited, so we can do that in Excel to get better visualization. So here we have different nodes, and we can come back to the page 1 and see what happens if we want to go from a path and plot our results in a path. So we go to the top view, and we can say, let's say here, which is in the middle. So we select this one, as we can see the nodes on the mesh here. So once more we go to the import and plot, and instead of the node we can select profile curve, and by clicking this one, create profile curve, you can create your own profile curve. So we want to create a profile from here, let's say like something like this. You can do it yourself and go node by node for a better outcome, but I want to do that roughly. So if we select one node wrong, we can go to the sequential undo, and we select this one and this one. So we created a path, and by clicking on this one we apply it, and as you see the profile curve is here. So we want to plot the temperature node on our profile curve. So we can either select a new window, or we can do the overwrite. So we do the overwrite and see the temperature gradient by the distance. So this is the temperature degree, and by distancing from left to right or right to left side of the weld, here we see the temperature is different. It is highest in the middle. So once more we come back to here. We can do this on the transverse direction. This path is really useful when we want to do the residual stress analysis, which are in next videos, but here we can see cool things like this. Alright, now we come back to the isometric view, and we can go through the phase change. So from the contour here we can do the phase change, and first phase here it is the first phase. We click on that. Right, so this is our material, which is the austenitic steel, stainless steel. So these are the austenite, and this is the filler material. So number 2 is the filler material. If we come to this side and we go further and further, we see that the material is all uniform by the end of the process. And this is a filler material that is fully used, so we have no residual of the material by the end of the process. So we consider this as we consider the parameters as a good parameter by seeing this result. What else we can do is to go to the contour. There are other things here. We can see the heat flux. This is the heat flux contour, which is not as useful as you see, but sometimes people need that. Or we have the grain size. I'm not sure whether this is accurate enough. And we have the object distance here. We can select that to distance to see that distance, but it's pretty much everything. So we did the thermal analysis of a 316 stainless steel L in 3D. The objective of this video was to do the calculation in a 3D model, so it's important to know the parameters and set the parameters. If you check the results and see there are any residual material left, so we can go further back and do the analysis again. Or if you want to make it perfect, you can select other parameters and see what happens. If we go with higher speed or lower speed, you get a really good understanding of the welding process you're working with. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any question, just ask me in the comments down below. I respond to every single one. Thank you. In this module, we are going to delve into residual stress analysis and welding. So we are going to learn the residual stress theory. What does this residual stress come from? How can we deal with it? How can we modify it? And you're going to learn how to do residual stress analysis of a MMAW, which is manual metal arc welding. And also we are going to post-process. We're going to look at the results and plot them. So to kick off, what is residual stress? The residual stresses are the stresses that remain in the material after the welding was complete and the material is cooled down to the room temperature. These residual stresses can cause distortion in the materials, and they usually came from the non-uniform heating and cooling in the material. Because the welding process is a very fast and rapid process, the heating and cooling down are non-uniform. It is not a transient process, so that causes residual stresses. Okay, the schematic of the residual stress is like this. Actually, it's like the figures of delta T and the stress. So imagine we are here in the line A, which is the base metal. As you see here, delta T is 0, so it means it is not affected by the weld. Then we have no residual stresses. Here, while the weld is hot and delta T is high, we see that the stresses are in this figure, something like this. This is not high. This is a very low stress because the material is still hot. And here, away from the weld pool, in the section C, we see delta T is lower and the residual stresses are like this. If we move from here to here, we see the high stress is in the middle and the cool down regions are kind of having the negative stresses here, but here we have the tensile stresses in the middle of the weld. And here in the section D, where the temperature is the delta T is 0. It means the material is cooled down. The weld started from here, and here is cooled down. We see high residual stresses in the material. So that's what happens inside a weld. Alright, what causes residual stresses in welding? The first and foremost is thermal expansion and contraction heating. During the welding and cool down, the welded area and the surrounding material expand due to the rapid cooling and heating. So the second one is cooling. The material contracts during the cooling, and the different cooling rates of different zones of the material, as shown before, cause internal stresses and residual stresses. The next one is phase transformation. During the welding, the material phases changes, and we have different zones of welding which contribute to residual stresses. And one of the most important one is the mechanical constraint. The clamps, the fixtures, or everything else that holds the material steady and constrain the movement can cause residual stress after being removed. Because if we look at this shape, this welded shape, you see here the material was clamped in the grip, for instance, and the material wants to it is melted, and it needs to be cooled down slowly, and it wants to expand or contract, and this grips doesn't let it to do that, and as a result it's going to distort and becomes a shape like this. So what effects can residual stresses cause? The first one is distortion. As I just said, it can bend the weld, like the shape you see right now, just before, and it can reduce the fatigue life because there is high stresses inside the weld, and in very low cyclic loading it can fail, and it might cause cracking, especially in the heat affected zone, or dimensional inaccuracies, which is the effect of the final dimension of the weld assembly, and we have fit up issues and we have to do the weld again. So how can we resolve this issue? Is to do the preheating. For instance, before welding, we can do the preheating. This preheating can slow down the cooling rate, so the material doesn't cool down faster while we're dealing with the material which is 20 degrees centigrade. And imagine that we do the welding while we did the preheating and it is already 100 degrees centigrade, and this can slower down the cooling rate, which is pretty useful and is one of the most widely managing processes in terms of residual stresses. The second one is post-weld heat treatment, or known as PWHT. They use that a lot after the weld was completed. They're going to heat that in order to release all those internal energies, and they cool it down in a transient way. The third one is pinning. Everything else that creates a minus stress, like this one. These stresses are in favor. We don't like it to be tension, so we want the pressure stresses, so we would like any process like pinning. So the next one is optimized welding sequences. So while we dealing with multi-pass welding, we should optimize the process. We should let the material cool down, or we can use the temperature of the previous pass as a heat treatment to the second pass, and we have to optimize the time, the temperature, and everything else. And the last but not least is using low residual stress welding methods such as laser welding or electron beam welding, and other processes. So in this simulation, we are going to use the same MMAW example, the 3D one, and we are going to do the mechanical. We're going to check the mechanical option, and we want to do a mechanical simulation, and we see that the residual stresses would be a shape like this. So without wasting any time, we want to go to the simulation software. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any question, just ask me in the comments down below. I respond to every single one. Thank you. So I opened the visual weld. Here we have the 3D MMA model, which was in the previous video, so take a look at it. So I open it. This is the model. Go to the welding advisor, and here we double check everything. It should be on solid, and these are 316 stainless steel, the material, and it joins with filler. The filler material is also 316, and we have here, this is the source and the weld pool, the numbers, the velocity is 3.5, 8.5, 10, 6, and 5 here, and the energy is as follows. And here we have the cooling condition, and the most important part is the clamping condition. As explained, these residual stresses having a direct relationship with the clamping conditions, so we have to double check here. There should be this side is on UX, this one is on UZ, and this one is U, X, and Z, and the time should be from 0 to 2500 for all clamping conditions, and we don't need a function database or thermal mechanical here. And here we should check this mechanical in order to have the residual stress analysis or mechanically analysis inputs. So we check this mechanical, and we generate input file, and click on yes. Now we want to solve. We click on 3D MMAW and we hit open. So here we have the box to do the analysis, and we don't need to check the thermometallurgical analysis. We only need to check mechanical, and we hit compute, and from here maybe we can do a multiprocessor analysis in order to finish the simulation sooner. So I use the maximum and enter. Now it is calculating. Alright, it is completed, and now we're good to look at the results. Okay, to see the results, we want to open the visual environment and go to the visual viewer. Here we go. We want to open the file. So if you look at the results, in the results section, previously we just only had post 1000 FTB. Now while we do the mechanical testing, we have post 2000 FTB. This is the code that the SYSWELD software has. So if we want to look at the mechanical properties, we want to open the post 2000, and if we want to see the thermal analysis, we can open the post 1000. It's a way to distinguish them. Right, this is the model we have here. Let's see the contour. Here we have different results, and we also can see the temperature results as well. So it means if you do the process, the mechanical, it contains more option. It not only has the temperature but also has the stresses. So we don't need the temperature here, but we want to go to the stresses. Here we have the element. You see the node element 1. This is the residual stresses after the weld was done. Here you see the highest stresses are here in the clamped sections, and if we look at it from, I think, this side, you see it is kind of bended. We can start the process and see it is kind of bended. Alright, let's look at other results. Here this is the XX and this is XY. You see the bending here is more visible. It's kind of distorted. Okay, we come back to the isometric view. Let's jump back to the stresses here. The node results, stress node. We have the von Mises stress, Tresca, and here we have the stress in XX direction, the XX stress component, and the thing that matters for us is to plot the residual stress. So we want to go to the file, and from important plot we can create a path here. So from instead of node, we go to the profile curves and we create a profile curve. Let's do a transverse, and from here we can go to the top view, and here in the center we can create a path. We carefully select all the nodes. So I would like to undo here. Oops. Let's zoom in and select. it was better that I selected the upper line, so it is still okay. We can see the trend. Alright, we created a path, and by clicking here and here we have our transverse one. We want to create another path in the longitudinal direction, so let's create a longitudinal path, and we can select. Right, we have selected a longitudinal path as well, and here it's better to determine the has region, and after that you can do residual stress analysis and see the results in the has, and as you see they would be probably much higher. So here from the transverse we are going to go from S stresses XX and plot in the transverse direction. As you see here, the trend is the same. If I was on the other line I told you, it might not be like this, but the trend is pretty much the same as what I showed you. In the weld direction we have pressure stresses here, and we have tension stresses here, and it is so high. And what we can do is to look at this, to plot the stress in YY direction. You see here, this is the YY stress in the transverse, and we can also plot the YY in the longitudinal direction. As you see, the trend is the same, and we can plot them in the XX direction. So as you see that the residual stress in longitudinal is not that much in the XX direction, but if you plot that in the has region you're going to have higher stresses. So we come back to the page one, and you see here the highest stresses should be here. So if you select it here, it would be better, because you see the path we selected doesn't contain the highest stress in the middle, and that's why we have a reduction. But generally it is okay. So if you are doing the analysis and creating the path, you can create this line, which is better. So that's it. It's pretty much everything. Now that you've finished SYSWELD Intermediate course, it's time to take it to the next level. Click on the video on screen before it ends to start SYSWELD Advanced Simulation, and I see you there.